Welcome to seminar 5. So my name is Aristarchus, and if you have any questions regarding this seminar, please shoot me an email. The topics which you'll be seeing in this seminar is like first order transfer functions, the second order transfer functions, dynamics, and a bit of Laplace transforms. So you can pause here and read the first question. I'll get into the solution. So I've summarized the information given here in the question. So the contaminant concentration increases according to the expression 5 plus 0.2 T, and the nominal concentration is given as 5 ppm. So which is C bar is 5 ppm, and the sensor dynamics in deviation variable form is C dash m by C dash is equal to 1 by 10 s plus 1 to find the time interval until which the alarm sounds after exceeding the environmental limit of 7 ppm. So there is an environmental limitation of 7 ppm, so we have to find how long it takes for the alarm to sound. If the nominal concentration is 5, then we have only a difference of 2 ppm there. Nominal, or the initial concentrations you can call it. So let's get into the solution. So let me mark. Okay. So the contaminant concentration increases according to this expression 5 plus 0.2 T, and the nominal concentration is 5 ppm. So if I write it in deviation variable format, which is C minus C bar, so the 5 goes away, and then what you have is C dash of T is equal to 0.2 T, and this shall be equation 1. And if I take Laplace transform, you get 0.2 by s squared. And in the question we have been given the sensor dynamics equation, and if I substitute C dash of s there, what I get is in here. And then to solve this and get the expression in terms of time domain, I have to split it into partial fractions, and then I have to take inverse Laplace transform, and then I'll get here. So I request you to try solving it. If you have any difficulties, you can ask me later. So you get the measurement. Cm is the concentration measured by the sensor, and with respect to time, simplifying this, what I get here is this expression, and this shall be equation 2. We know that the initial concentration was 5 ppm, and so the alarm will start sounding, because this is in terms of deviation variable, so the alarm should sound if it exceeds even by 2 ppm, because 5 plus 2 is 7. So substituting 2 ppm into this equation 2 and solving it, T becomes the independent variable, and if you substitute 2 is equal to this equation 2, and then if you solve for T, you get 18.414 seconds. So this is when the measured concentration Cm reaches environmental limit. But to see when the original concentration reaches the environmental limit, we have to go to equation 1, which was C dash of T equal to 0.2 into T. And if I substitute the same 2 ppm here, what I get is 2 by 0.2, which will be equal to 10 seconds. So the original concentration exceeds the limit at 10 seconds, but the measured concentration exceeds the limit of 7 ppm at 18.414 seconds. So the time taken for the alarm to sound after the actual concentration has reach 7 ppm is just the difference between these two. So if you take the difference, you get the time taken for the alarm to sound. So this completes question 1. Let's get into question 2. So a process of transfer function has the following transfer function: g of s is equal to y of s by u of s, and it is a second order transfer function, 2 by s squared plus s plus 1. For a step change in the input u of s is equal to 2 by s, sketch the response y of t. And we don't have to solve the differential equation, we just have to sketch the response and include as much as detail as possible, including the steady state value of y of t and whether there is oscillation. What is the decay ratio? So there are 2 sub questions, and let's see how to solve it. So we have been given the system transfer function, which is 2 by s squared plus s plus 1, to find the response curve when a step function is of magnitude 2 is given, and the decay ratio. So because we know that this is a second order transfer function, we compare it with the general form of a second order transfer function, which is k by tau square s square plus 2 zeta tau s plus 1. And then equating, we directly get k is equal to 2, and then tau square is equal to 1. So we take the square root 1 here, and we get tau is equal to 1. And then substitute tau. So 2 zeta tau is equal to 1, as we can see from the comparison. And then if you substitute tau there, we get zeta is equal to 0.5. Because zeta is less than 1, this system response to a step input will be oscillatory. So we'll have an oscillation because it is an underdamped system. For all the values of zeta less than 1, we have an underdamped response. For zeta equal to 1, we have a critically damped response, and for zeta greater than 1, we have an overdamped response. So if I plot it, it should be like this. So for this is for less than 1, and this is for zeta equal to 1. This is for zeta greater than 1. And then for computing the decay ratio, what we have to do is just plug it into the formula. So the formula can be found in your course material. So first we compute the time period with the formula given here, and we have all the values of tau and zeta. We just plug it inside, and then we get TP, which is the time to first peak, and then overshoot can be computed by the formula given here. We know the values, all the values. Pi is 3.14, so if you just solve it, you get 0.163. And decay ratio is overshoot square, so we just take the square of 0.163 and we get the decay ratio. The period of oscillation is 2 times the time taken to reach first peak, so we just twice of 3.6, which is 7.2. So we know that we are giving a step input of magnitude 2. So the response would be just because we know that g of s is equal to y by u, we just cross multiply. So we get y is equal to the transfer function into u. And then we can apply the final value theorem to compute the value of y of t at final time. And to compute that, what we have to do is we have to substitute the limit, because we have an equation in S domain. We use S tends to 0, S into y of s. So the response would, so we have the equation from the previous step, and S into y of s would be equal to 4 by s square plus s plus 1. And if we substitute s tends to 0, s square, this term becomes 0, this term becomes 0. So we have 4 as the final value. So the final steady state value would be 4, and the initial value is 0. And we know that this was an underdamped system. So if you sketch it, we have 4 as the final value, and then we have to just draw an underdamped response in such a way that it goes to 4. This is the solution for question 2. Now let's go to question 3. So let me choose the highlighter. A step change from 15 to 31 psi pressure units, pounds per square inch, results in a measured response, and the response has been given here. This is the response. Assuming second order dynamics, calculate all the parameters and write an approximate transfer function in the form. So this is just the reverse of question 2, where we have been given the response curve, and then we have to take all the characteristics of the curve, and then we have to find tau, zeta, k, and then we plug it into the general second order transfer function form to get the second order transfer function. Let's see how to solve this problem. Switch to the pen here again. Yeah, we saw from the question that the step change in the input was from 15 to 31 psi. And from the response graph, we can see that the output y changes from 8, which is the initial value, and 11.2, which is the final value. Let me write final, I for initial. So the process gain is the change in y by change in u. So 11.2 minus 8, which was the initial value, by 31 minus 15. So if you compute, you get 0.2 mm/psi. And I've just given an image here. So overshoot is equal to A by B from the graph. So here, which is the peak minus the steady state value by the steady state value minus initial value. Yeah, so P for peak minus steady state by steady state minus initial value. So overshoot can be computed from the graph. So peak is 12.7, and then the steady state value is 11.2 by 11.2 minus 8, which is the initial value. So if you compute that, we have overshoot as 0.47. And then we know the formula for overshoot. So if you equate the formula to 0.47, the unknown variable is zeta here. So if you solve this, you get zeta is equal to 0.234. So now we know the zeta. And we have one more, which we haven't used. We have the time period, which is 2.3 seconds. So, yeah, so we have the time period of oscillation, which is 2.3 seconds, and we know the formula for the time period, and we have already computed zeta, so the only missing variable is tau. So if you plug in all the known values and equate for the unknown variable, we get tau is equal to 0.356 seconds. So now we have k, tau, and also zeta, so we just substitute everything into the general second order transfer function to get the final solution. So this was just, we went in the reverse order. We had the graph, response graph, and then finally we computed the transfer function. So you might be tested in both ways in your exams. Let's go to the final question of this seminar. So let me change it to red here. Given the second order plus time delay transfer function, e power minus 3s by 10s plus 1 into 2s plus 1. So we have to approximate the time delay using 1 by 1 Pade approximation to get a new transfer function. So that is question 1. And then analyze the step response dynamic behavior, stability and oscillation. Let's do that. So the formula for 1 by 1 Pade approximation is e power minus theta s is approximately equal to 1 minus theta by 2s by 1 plus theta by 2s. So here theta is 3. So theta by 2 is 1.5. So we have the transfer function, and then if we apply Pade approximation, what we get is this. So this completes our question 1. So we have the new transfer function. Now we have to do the stability analysis. So to do the stability analysis, we have to compute the poles and the zeros of the transfer function. To compute the zeros, we equate, if this is, we equate the numerator to 0 to compute the, so if n is equal to 0, we get this, all the zeros of the transfer function, and if d is equal to 0, if we equate the denominator to 0, we get all the poles of the transfer function. So poles are minus 1 by 10, minus 1 by 2, and minus 1.5. And we see that all the poles, so if you plot them, so this is the left half plane, and because all the poles are negative, they are going to lie on the axis, and they don't have an imaginary part, so they will lie exactly on the axis. So any pole on the left half plane is considered to be a stable pole. So all these poles are stable, and these poles do not have an imaginary part, so there will be no oscillation. So this is a stable system, and there will be no oscillation in the response. And this completes our sub question 2. So we have completed question 4 as well. So thank you, and if you have any questions related to this seminar, please drop me an email. I'll see you guys in the next seminar.